All right, so now we've had a background in all kinds of new stuff. We're going to take a look at some atomic structure, periodic trends, and molecular structure, and this is a little bit of a throwback to grade 11 when we talked about the periodic trends and all that kind of stuff. And so some of this stuff will be familiar to you, but we're going to now look at it in light of some of the new theory that we just learned. So for each of the following, we know periodic trends of each, and we have to be able to explain why the trend exists. All right, so let's take a look at atomic size. So atomic size is determined by the balance between the forces of attraction of the electrons that they feel towards the nucleus and the forces of repulsion they feel for each other. All right. Ionization energy, we talked about that last year. It's the amount of energy required to remove the outermost electron from an atom. We talked about electron affinity, the amount of energy released as an atom gains one electron. And electronegativity, a measure of one atom's ability to remove an electron from another atom. Now, that's all grade 11 stuff. We can remember that? Yes? I hope so. If not, you might need to dig back and relearn some of these things. All right, so let's take a look about intermolecular. So the attraction between between molecules, not within an atom, within a molecule between the atoms, but between the molecules, right? So this is intermolecular forces that we're talking about here. So the weakest ones are the van der Waals or London dispersion forces. Both names are used interchangeably. They really mean the same thing. Very weak forces of attraction. They exist between molecules of a molecular compound. The strength of these forces increases with the size of the atom and the number of atoms in the molecule. These forces can be described as instantaneous dipole-induced dipole. As the electron density in a molecule shifts, one side of the molecule becomes momentarily more negative than the other side. Thus, an instantaneous dipole is created. If this molecule is close to another molecule, this dipole will induce a dipole into its neighboring molecule, and these two molecules would then be held together by an instantaneous dipole-dipole attraction. It lasts only a moment, and therefore it's very short-lived, and pretty soon the molecules it dissipates, and the molecules are again without a dipole, so non-polar. All right, so so we have, let's say, between neon atoms, we have a neon atom. They are essentially electrically neutral. Electrons are dispersed evenly overall. They come close to each other. Perhaps there's a momentary shift of electrons to one side of the atom over the other. And so then we get a momentary dipole. This end is slightly negative, this end slightly positive. What it does is this positive end then attracts electrons to this side of the neon in this atom. And so then it creates a momentary dipole in this one. And so now we have a little bit of attraction between these neon atoms. They're very weak attraction. We need to understand that. And it's very short-lived because these electrons are moving around, and so then this dipole slowly dissipates, and then, or very quickly dissipates, and then momentarily it's gone again, and we're back to two normal neon atoms. All right, so that's the London dispersion forces. Very weak. It accounts for most molecules or atomic atoms where we have gases at room temperature, very low melting points and boiling points, that sort of thing. The dipole-dipole attractions are the next strongest attractions that we have between molecules. This is the force of attraction that exists between two polar molecules. All right, so the partial positive end of one molecule is attracted to the slightly negative end of the other polar molecule, and so there's a slight attraction between them. They're stronger than London dispersion forces because they don't disperse. Those dipoles are permanent, and so they always exist. Those dipoles in those polar molecules don't go away, and so the attractions are always there. All right, and so the positive end of one here is attracted to the negative end of a neighboring molecule. So that raises your melting points and boiling points and that sort of thing. Now we have polar molecules that have hydrogens and oxygens, or hydrogens and nitrogens, and those create what we call hydrogen bonds. And the hydrogen bond is so strong, it's almost a bond on its own. Now it's not as strong as a covalent bond, but it is still a fairly strong attraction. So it's a special kind of dipole-dipole attraction, very strong force of attraction that exists between the slightly positive hydrogen on one molecule and the slightly negative oxygen on a neighboring molecule. Or it could be a hydrogen, or it could be a fluorine. Usually those three are the only ones that have hydrogen bonding. And it's the lone pairs of electrons that exist on these guys, the oxygen, the nitrogen, and the fluorines, that are, well, fluorine doesn't usually have a lone pair, but the electrons on the fluorine that have the attraction to that hydrogen. Okay. The dipole-dipole attractions are about 5 times or more stronger than normal dipole-dipole attractions, but they are still weaker than covalent bonds. Okay, so covalent bonds are kind of the next step up. If we were to draw, let's say, water is kind of a classic example where we have hydrogen bonding. So the one of the lone pairs from the one oxygen is attracted to the hydrogen of a neighboring water molecule, and then that creates what we call the hydrogen bond. Hydrogen bonding is also responsible for creating what we call the hydronium ion in acids. All right, so that's kind of another thing to think of, where hydrogen is physically removed and kind of attaches itself onto here to create a hydronium ion, and that again is one form of this hydrogen bonding, or the extreme form of this hydrogen bonding. All right, so the range then, as we're kind of moving down then, now once we get to covalent bonds, the next one is ionic bonding. And ionic bonding is, of course, the electrostatic attraction between ions, so positively charged and negatively charged ions. And that attraction is an electrostatic attraction that is very strong. It's the strongest of all of our bonding types here. However, there are some arrangements of covalent bonds that are even stronger than ionic bonds. So we can get into these scenarios where we have the covalent bonds. So the bonding is described as we did in the previous note, where we talked about the overlapping of orbitals. So that's why we have these kind of regions now described with these spherical arrangements in these types of molecules. So it's the overlapping between valence orbitals that creates these bonds. So hydrogen fluoride versus hydrogen iodide. We have a greater overlap between hydrogen and fluorine than we do with hydrogen and iodine, and therefore there's a stronger attraction between the hydrogen and the fluorine than there is to the hydrogen and the iodide. Similarly, if we look at the overlapping of the orbitals between, let's say, fluorine and iodine, molecular iodine and molecular fluorine, similarly here there's a greater overlap between the fluorines because they can get closer together than there is between the iodines, which necessarily have to remain further apart. And so the greater overlap creates a stronger attraction. So it would take a whole lot more energy to pull the two fluorines apart than it would to pull the two iodines apart, that sort of thing. Metallic bonding is kind of a bizarre one. A little tough to explain. However, what happens in metallic bonding is that the metals themselves are attracted to the electrons. So the nuclei of one metal is attracted to the electrons of a neighboring metal atom. And the electrons then, because they don't really care about which atom they're attracted to, because an electron is an electron is an electron, we end up with the electrons free to pop from one to the next. So if there's one electron leaves, for instance, it creates a kind of a hole, and a neighboring electron, whatever's around, kind of pops in to fill that hole. And so we have this sea of delocalized electrons, which normally we don't kind of notice until we, put some electrical wires on there, and suddenly these electrons can move freely through that particular material. The strengths of okay, so this is kind of an important part here. The strengths of the attractions within molecules determines the chemical properties, whereas the attractions between molecules determines physical properties. Okay, let me say that again. The strength of attractions within molecules determines chemical properties. The strengths of attractions between molecules determines the physical properties. Okay. All right. Now we have another thing about crystalline solids that are ordered in a regular repeating pattern. We have two types. We have ionic crystals, where we have that crystal lattice that we talked about, so sodium chloride, salt crystals, calcium chloride, sodium nitrate, those kinds of things. Because the attraction between the positive and negative ions is so strong, we have really high melting points, we have really high boiling points. These compounds are usually very hard. They're brittle as a result. Okay, so they generally fracture along clean faces, that sort of thing, because it's a regular crystal lattice structure. If you dissolve them, so they dissolve most of the time, not always, but when they dissolve, they conduct electricity because you've got ions that are free to move charge around. Okay. Molecular crystals are a little bit different. The molecules are held in a crystal lattice similar to what the ions are held into. But the intermolecular forces are quite a bit weaker. Molecular crystals tend to be soft with low melting points. They don't conduct electricity like liquids and solids, as liquids or solids. And they don't generally dissolve in water. When they do dissolve in water, though, if they're polar substances, then because the molecule doesn't allow for charges to be developed or for there to be free electrons in that environment, they don't conduct electricity. Now, we get to a couple of molecular compounds which are, the structure is such that they form what we call a network covalent crystal, or a network solid. What happens here is that the lattice sites themselves are occupied by atoms that are covalently bonded together, and they actually have a harder substance. They actually form a harder substance than even ionic crystals do, because the covalent network now is like all of these atoms are actually covalently bonded to each other. It's not a molecule that is attracted to a neighboring molecule. It's this crystal structure is actually one huge molecule. Examples of this are diamond, silicon carbide, silicon dioxide. Those three are the kind of the three main ones that will form these network solids. Essentially, diamond is pure carbon. It's the hardest form of carbon. Carbon will also form other configurations which are also network solids, not as hard as diamond, but still network solids in different forms. You may have heard some of them: graphene, graphite, buckyballs, nanotubes, all that kind of stuff. They're network crystal structures of carbon atoms. And it's really just one giant molecule of carbon, which creates these great big lattice networks that are really, really hard solids. Okay, so these are the three toughest ones, diamond being the hardest substance on Earth, silicon carbide being next, and then sand or silicon dioxide being the next one. We then have metallic crystals, which metallic crystals have positive ions at the lattice points, and they're surrounded by a sea of delocalized electrons. Metallic crystals have a luster. They conduct electricity as a solid or a liquid. Some examples: copper, silver, iron, sodium, mercury, these sorts of things. Okay. All right. Try these homework questions that are related to this. Bring questions to class. I'll try my best to answer those.